Hello everyone, my name is Siham Jamal from the Laboratory of Intelligent System Design at Abdelmalek Saad University in Tetouan. Today I'm glad to present my work titled Large Language Model in Healthcare, a review. In this talk, I'll give a brief overview of the current state of medical large language models. So let's begin with a short introduction. In medicine, doctors have to make decisions quickly and accurately. They depend on their knowledge and experience to analyze a huge amount of patient data. But with the growing volume and complexity of this information, it's becoming harder to process everything in a short time and still ensure reliable results. That's where large language model can really help. This model can understand and generate text, and they've also started to analyze medical images, combining both text and visual understanding. However, most existing models like BERT, T5, Palm, or Llama were designed for general language tasks, not for the specific logic and terminology used in healthcare. So researchers have started developing specialized medical LLMs that can better understand clinical language and reasoning. And this leads to the main goal of my presentation to review the current state of these medical LLMs. More specialized, this presentation aims to describe the main approach used to develop medical LLM, highlight the key clinical tasks performed by their specialized models, and discuss the main challenges that still limit their real-world clinical adoption. So, through this review, I aim to give a clean picture of where we are today. In this part, I'm going to talk about the main approaches used today to develop large language model in the medical domain. Overall, we can group them into four main strategies: fine-tuning, prompt tuning, continual pre-training, and training model completely from scratch. So let's start with fine-tuning. This is one of the most widely used methods to adapt a general language model to the medical domain. The idea is to continue the training of a pre-trained model using a smaller but more specific data set, usually labeled data for a certain task. So in full fine-tuning, all the model parameters are updated, while in the parameter efficient fine-tuning, we only adjust a small number of them. This makes the model more efficient and still very effective for medical tasks. So a good example of fine-tuning is clinical chemo. It was fine-tuned on more than 170,000 synthetic conversation between doctor and patient using Llama 2 as base model, but with only part of the parameter updated. Another example is Chat Doctor, which used around 100,000 real patient-doctor dialogue and updates all of Llama's parameters. So both models can handle medical question answering and clinical dialogue. Normally, large language models are trained with objectives like masked language modeling or causal language modeling. Their goal is just to predict the next or missing word. This is great for language understanding, but it doesn't match what clinicians actually need. In medicine, we don't just complete sentences, we follow instructions like summarize the report or suggest the treatment plan. That's why we move from classic fine-tuning to instruction fine-tuning. We teach the model to respond to specific clinical prompts. For example, Radiology GPT learn to turn radiology findings into clear impressions, so the model behave more like a medical assistant, not just a text predictor. Now, instead of updating the model's parameter like in fine-tuning, prompt tuning keeps the original model frozen. So we just add a small set of learned parameters called soft prompts. that are trained to guide the model toward a specific domain or task. It's an efficient way to adapt a large model without retraining it completely. So a good example, the example is MedPalm, which builds on FlatPalm using the multimate question answering dataset with prompt tuning and instruction tuning combined. The model can understand and answer complex medical questions with much less training effort. The next approach is continual pre-training, also called domain-adapted pre-training. So, unlike fine-tuning, which uses small labeled datasets, continual pre-training uses large unlabeled medical corpora, such as clinical notes, biomedical papers, or research abstracts. During this process, all model parameters are updated, allowing the model to deeply absorb medical language and knowledge before fine-tuning. For example, MiLama. So this model continues Llama's pre-training on massive clinical and biomedical data. Then it's fine-tuned for specific text analysis and reasoning tasks. Another example, PMC Llama is trained on millions of academic papers and textbooks and later fine-tuned for biomedical question answering. Then cancer LLMs focuses on oncology. It was continually pre-trained on clinical notes and pathology reports, then fine-tuned for diagnosis generation and phenotype extraction. So continual pre-training updates all parameters with unlabeled data to build strong medical knowledge, while fine-tuning refine this knowledge for concrete clinical applications. The last approach is training from scratch. In this case, the model doesn't reuse any previous knowledge. We only keep the architecture, but all weights are initialized from zero. The model is then trained entirely on domain-specific medical or biomedical data. This process is very costly, but it allows the model to learn the language and structure of medicine from the ground up. For example, Medbird was trained from scratch on millions of electronic health records, and it's used to predict diseases such as heart failure or pancreatic cancer. Then DNA BERT was built using genomic sequences instead of normal text. It learns the pattern of DNA bases and can predict parameters or transcription binding sites. Finally, PubMed BERT was trained on 14 million biomedical abstracts from PubMed. It performed well on tasks like named entity recognition, relation extractions, or question answering. However, training from scratch has become very difficult to use today because most modern models have billion of parameters, which make file training extremely expensive in terms of data and computation. This table summarizes recent medical LLMs according to their training approach. As we can see, the trend is moving toward hybrid strategies combining continual pre-training with instruction tuning to balance medical knowledge and task performance. Now, let's look at the main clinical tasks performed by a specialized large language model in healthcare. This model can handle two main categories of tasks, fundamental language tasks and clinical application. The fundamental language tasks like named entity recognition, relation extraction, text classifications, and semantic similarity. They are common to general LLMs, but they are essential for understanding clinical language and extracting medical meaning from text. Then we have the clinical applications, which bring the model closer to real medical practice, such as medical question answering, dialogue system, report generation, and clinical decision making. And as shown in this diagram, so most models perform best on question answering. Well, results vary from other tasks like dialogue or report generation. And when it comes to decision-making tasks, for example, suggesting a diagnostics or treatment, performance is still limited. So today, medical LLMs are quite good at understanding and answering, but not yet at reasoning and deciding like a clinician. Finally, when it comes to real-world use, large language models in clinical practice still face several important challenges. First, there is the issue of explainability and transparency. So clinicians need to understand how and why a model makes a decision. And without that, it's very hard to build trust or encourage adoption. And second, these models often rely on data of variable quality, which can introduce errors and biases. Even more, some models actually generate part of their training data using other AI systems. So any mistakes or hallucinations in the first model can easily be passed on to the next one, which can be dangerous, especially if the output is used directly by patients. Another major issue is the lack of standardized evaluation benchmarks, making it difficult to compare models or measure their true clinical effectiveness. And finally, we still face language limitations and prompt dependency. So most models are English based and highly sensitive to how a question is phrased. So before LLMs can become truly a reliable partner in healthcare decision making, these challenges must be carefully addressed. Thank you for your attention.